It's my pleasure and honor to introduce you to the MITRE Corporation's Early Career Research Program. For the past 3 years, MITRE has invested $1 million each year to develop science, technology, engineering, and mathematics leadership. Created within MITRE's Innovation Program, the Early Career Research Program helps develop critical leadership skills, including how to perform research, how to manage a research project, and how to communicate results effectively. The Early Career Research Program is highly selective, and each participant pursues a particular research challenge under the careful guidance of an experienced research mentor, often simultaneously pursuing an advanced degree. Many participants work half-time on the direct program, accelerating transition of their research to MITRE sponsors. Now in its third year, the program has contributed to the development of 20 extraordinary individuals. Prior participants have had their work externally recognized, for example, as best papers at conferences, and even acquiring direct funding from the government. So, please lean forward and enjoy meeting one of MITRE's early career researchers.
Hi, I'm Marco. I'm a mathematician working at CASD, and today's talk really involves perhaps more advanced data kind of science methods. Thank you. More advanced data science methods by understanding this concept of low rank. So I'm going to begin this talk with a kind of a quiz or a challenge for all of you guys. So here is a 2D data array, or a matrix, as I'll refer to it. And your challenge is to figure out what's so special about it. Is there something hidden there? Is there some structure that you notice? Okay. And so it's an engineering faux pas, I know, because there are no labels on the axes. No color bar, no title. That's cool, and that's fine, right? Just imagine that this data set is your own, right? If you work in healthcare, maybe the columns represent patients, and the rows represent various answers that they gave to a questionnaire. Okay. If you come from CASD like me, maybe the rows, maybe the columns represent airports, and the rows represent something like metrics that we care about, like on-time arrivals, on-time departures. Okay. So now's the big reveal. It turns out with this matrix, all the rows actually follow the same pattern, this 1D vector, or data array here, just scaled differently according to this vector that you're seeing here. Right? So basically, you could generate this entire data matrix from these two vectors. And I'm going to call them keys just for brevity for this talk. Okay. Mathematically, this is what we call a rank 1 matrix, okay, and that's important. And it's also trivial to extend this concept to a higher rank matrix. So if I add a rank 1 matrix to another rank 1 matrix, we'll get a rank 2 matrix, and each of these matrices you see here have their own generating keys. There, okay? So here's the part of the talk where I'm gushing, I'm really excited, I'm smiling, and I get this glazed look from the audience. No one's polite enough. Well, everybody's polite, actually. No one will say who cares. But you know, this is a question that needs to be answered, right? And it's fair. So why is this important? The first reason is really apparent, and it's obvious. It's a form of data reduction. Instead of storing the whole data matrix, right, I could get away with just storing the keys. So now you're storing m times n, right? Instead of m times n elements, you're storing m plus n elements. That's important. But more importantly, right, it's kind of a form of modeling. Once we know these keys, these generating keys, we can do a lot of great things. And I'm going to go through some examples. The first of which is how to infer missing data. Say these holes were present in my data set, as you can see here. But it's not really pertinent anymore because we have the keys and we know what to do with them, so we could patch up those holes. This is actually pretty useful and has been used in the literature before. I can't believe it, but it's almost been a decade since Netflix launched their challenge, right? So they gave you user data. So here on the x-axis are the users, and the y-axis are the movies, and they gave it ratings. Obviously, the users didn't see all the movies, nor did they rate all of them. It is now your job to figure out what movie to recommend to them next that they have not seen. But this is just a data matrix that's full of holes, right? So what's the low rank assumption here? If we understand that really, if people have similar personalities, there's a good chance that they'll have similar tastes in movies. Right? We could actually leverage this low-rank technology to complete this kind of gappy matrix and make our recommendations for movies. Moving on. So say I decided to salt and pepper this data set maliciously. So now there are these orange boxes that don't belong there. So this isn't, again, a big deal anymore because we have the keys, the data keys that generate the data originally. So we could actually just do a comparison, and by doing a simple difference, we could pinpoint which of those salt and peppered, which are the malicious points and which are not. And this pops up in two applications. The first of which is in video surveillance. So we see here we have 3 columns. The first column, the original frames from an actual video feed. Right. And so we see it's being decomposed into 2 parts. The middle column is the low rank part, which is what's generated by those keys I mentioned, and a sparse part. So it's kind of wonderful that you could see here, right? The low rank part basically corresponds to the static part of the video, and the sparse part corresponds to the people moving. So it depends on what your analysis is, what you'll pay attention to. If I were, say, analyzing how people move through grocery stores or malls, which people do, I would be interested in the column C, the sparse part, right, which is tracking the movement. But if I were looking for, say, shifty characters, maybe I'll pay attention to that guy who's just not moving in the middle column there, right? Why is he not moving? How long has he been standing there? Is that normal? Right? So as an analyst, the mathematics can only take you so far, right? You have to really interpret the output of the mathematics also, and that's really a good lesson here. And here is a live demo of actually the same setup, but now it's an escalator scene. Can we play this, please? Wonderful. And you can see here, right, it's the same setup. Now the people getting on the escalator are being singled out, and the escalator is being singled out as the low rank part. Okay. So we could also take this concept of low rank structure and apply it to, say, the airspace. So I don't know if you guys know this. Every time your plane kind of lands into an airport, most likely they'll actually, let's take Dulles as an example. Every time a plane lands in Dulles, right, they will be taking one of these set paths to land at Dulles Airport. These are called procedures, right, arrival procedures. And during my fellowship, I got to kind of explore some of this data thanks to CASD's big data initiative. And I made the following hypothesis. I said, I bet that how often and how well flights follow these paths, really this data set will be low rank. Why is that? Because only few patterns really dictate the shape of the data. Right? So there's a significant shift in weekend versus weekday traffic, for example. If we were to visualize what that data looked like, here's our matrix. The procedures are on the left, the names, right? And you can see on the x-axis, we're only considering the first quarter of 2012. And obviously, the color bar tells you about how many flights were conforming to the particular procedure. If we use the same kind of idea of separating this matrix into a low-rank part and a sparse part, we could examine the sparse part for unusual deviations to what we expect. Then it becomes really apparent where traffic was higher than expected. And there are also little blips that you become aware of, like this guy right here. Right. That is an anomalous day of traffic that was identified by this technology, and we could compare that to a normal day, and we could see immediately that there are some flights emanating from the south that shouldn't have been. Right. Finding, quote unquote, what's normal and what's abnormal, it typically is a manual process, right, led by analysts, a talented analyst here at CASD. And I think this will allow us to help automate that, because the analysts really need to be figuring out why were there flights flying down from the south. Is this posing some sort of safety hazard? Right? They need to be spending their time kind of drilling down into these events rather than looking for them. So this is an advanced capability we're working on at MITRE CASD. And with that, I wanted to move on to the last part. So one more thing that you could do with this idea of low rank is really you could exploit it to perform classification or clustering. In this toy example, it's a little apparent what your clusters or would look like, right? So that left vector there almost gives it away for you, to you. But let's look at the less trivial example. And so the example I actually did research on this past year also was analyzing air traffic controller utterances. So if you guys don't know, air traffic controllers talk to pilots a lot, right? So the air traffic controllers might be telling the pilot, you need to slow down your plane now. Right? Pilot will respond, okay, I'll slow down for safety reasons, etc. And during the course of a day, hundreds of millions of these conversations take place. Right? The thing to note, though, is despite the fact that there are a vast number of utterances, sentences spoken, they really only fall into a few topics. In this particular case, right, this air traffic controller might be saying a lot of things, but really he was only talking about two things, altitude-related things and speed-related things. Right? So in some sense, what air traffic controllers say is low rank in topic space. So I advanced this research, and so now we have at CASD an algorithm that will take an utterance like this and automatically assign a topic to it. So this is a particular case where an air traffic controller is transferring control of one plane to another air traffic controller. Here's a different example. So I'll read it for you guys, since the contrast is a little bad here, but basically, excuse me, the air traffic controller had noted that there is some choppiness at 39,000 feet, and he is asking the pilot, do you want to stay at your current altitude, 37,000 feet, or do you want to try for that choppy 39,000 feet? And the algorithm correctly identified that this is an altitude-related sentence, despite its complex structure. Also tried to trick it by giving it sentences with no contextual value, like say, thank you. It correctly said that that doesn't belong to any of these topics that we care about. Okay. So furthermore, what's great about having this capability is now we could marry these labels to a rich trajectory source at CASD and produce these types of like heat maps, basically saying, well, where are the air traffic controllers telling pilots to slow down or speed up a lot? Right? Why is that happening? Right? And the FAA really wants to know, right, after investing multiple millions of dollars, right, how effective was this airspace redesign? And tools like this, I think, will put MITRE and CASD in a great position to answer those types of questions. Right? And if you guys are curious, you could follow this reference at the bottom. So by now, I hope I've changed your mindset and kind of the question, right, from who cares to, well, you talk about these keys, but how do you find them? And in fact, it's true. I just took for granted that you kind of knew what the keys were up front, but of course you have to discover them. And it's basically, I'm just going to refer you guys to some technologies that are enabling here, right? Say you had access to the full data set, and it's of reasonable size. You could try the standard, classic, tried and true methods, principal components analysis, singular value decomposition, and non-negative matrix factorization. If your data happen to have some gaps, right, you may want to consider something called robust PCA and also read up on something called the nuclear norm minimization. So now I'm going to conclude. So I hope I've convinced you that knowing about low-rank structure allows for some really magical things, obviously caveated with only in data analysis land. And you know what's great is that this low-rank structure is surprisingly present in many of the data sets we deal with at MITRE. The only right, supposition is that your data needs to come in a 2D array or a matrix. We've talked about a bunch of applications, recommender systems, video surveillance, airspace analysis. Notably missing was healthcare, but I hope those of you who are kind of practitioners of data science in healthcare could see where this could be applied in that particular domain. And finally, just a note, I think this technology is great. Obviously, I'm gushing about it right now. But just please do keep in mind that it's just one set of tools that we have for data analysis. There's no such thing as a silver bullet in machine learning, and we all need to be aware of that, right? And as with any algorithm, right, the output needs to be balanced with a lot of our domain expertise, right? That's kind of the recipe of how we could bring value to our sponsors. So with that, I'm going to close my talk. Thank you.
Thanks for an interesting talk. The restriction to 2D array, I think, is based on the particular two characteristics that you've chosen, and in general, it could be a larger dimensional reduction based on 3 or 4 or whatever.
Absolutely.
Can you talk about possibly other characteristics that could be used in the same vein as the 2D array?
So actually, that's a great question. And so for simplicity of the talk, right, I'm telling people about 2D arrays. But in fact, a lot of these technologies, the frontier now is actually using them for 3-dimensional arrays, so-called tensors. And all of these technologies, you have to be wary also mathematically and computationally how you might change the structure of the math. But there are actually analogous kind of like analyses for those type of multi-dimensional arrays. I mean, greater than 2, of course. So that's a really great question. In fact, I believe that that's kind of the forefront of the research now is how do we take these technologies and extend them to, like, say, tensors, again, the 3-dimensional arrays, which do pop up. And if you're very naive about how you deal with them, it will, well, you'll either get garbage or you'll take forever solving the problem. So
I'm not sure what the answer will be, but I know that there's ways of mapping multi-dimensional data into like 2-dimensional space. Is that anything that has been done in this area? Like, would it perform well using something like this, or would it have similar performance, or what do you expect? Right.
So usually when we map multi-dimensional data to arrays, so like you just say, well, let this column be like, 1 dimension of the multi-dimensions, right? So now one row is multiple dimensions, but you have to basically ensure that your data is consistent in the sense that they all have the same dimension, right? So you can analyze, say, something that lives in 4 dimensions and then something that lives in 5 dimensions all at once using this approach.
Is MITRE currently exploring how these data analysis techniques interact with emerging big data platforms such as Hadoop and its likely successors?
So that's a really great question. In fact, MITRE, I could tell you, MITRE Kazi, we were looking into it. I think that there are some challenges implementing this in the big data world. So in big data world, basically, some of these technologies are computational, have a computational complexity of n cubed, which is unacceptable when you're doing big data, right? So you have to basically rely on iterative approximations, and these types of implementations really need to be kind of realized in the upcoming months, I'd say. But we're basically at the evaluation phase currently, at least at MITRE Kazi. So I'm not in a position to speak about the rest of MITRE.
I take it these are relationships that are strictly linear?
Yes. So there are tricks that you could use to say like the kernel method so that you don't necessarily have to assume linearity. But for the most part, inherently, when you're dealing with matrices, they're usually used for linear relationships. But you could use, again, certain mathematical techniques like the kernel trick to basically extend to nonlinear regimes.
So, Marco, I'd like to ask the same question I asked Ellen, which is, what did you find most challenging? What did you enjoy the most? And then any advice for other young researchers?
Thank you. Let's see. Most enjoyable. I hope if it wasn't apparent from how much I'm smiling right now, how much I like this. So the fact that I got to do this for a year full-time and really learn about the state-of-the-art technologies in mathematics has just been wonderful. I think the challenge, in fact, is not learning about these new technologies, but really marrying them to needs that we have and our sponsors' needs. I'm lucky enough to be able to engage, like, say, my mentor, Glenn Roberts, who's been really helpful in at least providing guidance in that particular aspect. But I think that it's always a challenge, right? You have this wonderful tool. how can I use it to help the sponsors? And I think that's the challenge for all of us, and I thought that that was the most challenging part of this year. Advice for new ECR peers, I would say that definitely keep writing. Keep a running tab and just write about your research, because ultimately you're going to churn out papers or MTRs, and you want to have some idea of what you did and what worked, what didn't work, right? Even if your research wasn't successful, you could produce a lessons learned document. And if it was successful, you could publish it. So I think it's worthwhile to just kind of keep a running journal, if you will, a research journal. And I found that to be really useful in my case.